Okay, moving on for number 9. 10 I might skip because 10's a bit more convoluted than it seems. So number 9, we're focusing on the arc length, if this is the angle. Now keep in mind this. Arc divided by the radius is equal to the angle. So in this case, they want to know the arc. The radius is 65, and then the first angle, it's 19 pi over 20. So if I multiply both sides by 65, I get that. So the arc is going to be equal to 19 times pi divided by 20 times 65. Or if you want, 19 times pi times 65 divided by 20. And that'll be the arc length. Does that make sense? Yes, it does, because this here is almost 1 complete pi. If you look at the arc length of 65 of a circle, or sorry, radius 65 of a circle, the whole way around should be 2 times 65, so 130 pi. If you take 3 times that roughly, we're talking about 3.14, it's roughly 400. So 1 full way around would be 2 pi, and half of that would be 1 pi. Since this is almost 1 pi, half of this is 200, which is very close to our answer, which means that's very much likely. So how do we do the rest of them? They're all the same. The second one is given in radians without pi, but it's still arc divided by 65 is equal to that. When I multiply that both sides by 65, I get the arc is equal to, let's see, 30. We'll just get it to do it. 1.25 65. So the arc length is going to be 81.65 centimeters, which also makes sense. So this is for B, which are centimeters, which also makes sense because 1.25 radians is roughly a third of a pi. Pi radians is 3.14. A third of a pi is a third of 180. A third of 180 is roughly 60. And 60 should be roughly slightly more than the radius, because 54 should be the exact radius. So since that's around 60, that number makes sense. 150 degrees, we should convert it. So what's 150 degrees in radians? You have to multiply by pi and divide by 180. Zeros disappear. Both are divisible by 3. 5, 6 pi. So 5, 6 pi times 65. So 5 times pi times 65. Divided by 6. Gives us an arc length of 170. Does that make sense compared to the other ones? 170 centimeters. Yes, it does, because 150 degrees is almost 180, and we already determined earlier that this is almost 180 as well, and resulted in 190. So this should result around 170. 10, like I said, we're going to skip. We'll go straight to 11. A wind turbine has 3 blades, each measuring 3 meters from the center. So that just means we have a 3-meter radius circle. Like this. Just pretend there's some blades in there. Like that. And they measure 3 meters from the center. At a particular time, the turbine is rotating 4 times a minute. 4 times a minute. So how many times does it rotate? Once. Well, if you do 4 times a minute, 60 seconds, if I divide this by 4 and this by 4, it would be 1 time is equal to 15 seconds. So it only takes 15 seconds. Let's figure out how far the tip of the blade has traveled. For this, in 5 minutes. So 5 minutes, if it takes 15 seconds to do one, let's figure out how far it travels in 15 seconds. So if I go here and go around once, I've traveled 2 pi r distances in meters. 2 pi r, and r is 3, so 6 pi. So that's how far I travel, 6 pi meters, in 15 seconds. Since 5 minutes is the equivalent to 20 15-second periods, in other words, 20 rotations, then I travel 20 times 6 pi meters, or 120 pi meters. That's the exact answer of how far I've traveled. But if I want to put it in whole numbers, which will be less accurate, you do 120. Why is it less accurate? Because any number that keeps on going forever, I have to cut out at some period, and therefore becomes less accurate. For instance, if I cut it out here, that's not the exact number, is it? So we've answered B. Determine the angular velocity in radians per second. Well, we've already determined that it takes 15 seconds to go around once. It does 2 pi radians per rotation in 15 seconds, so it does 2 over 15 pi radians. If you wanted to put that in numbers, 2 times pi divided by 15, it does this many radians. So that would be the angular velocity, radians per second. Radians per second. There you go, that's 11. 12, a wheel's rotating at an angular velocity, so they're telling us how fast it's going. Now ask yourself, okay, while a point on the circumference of the wheel travels 9.6 pi meters in 10 seconds, how many revolutions does the wheel make in 1 minute? Okay, if it's going this many radians per second, minute would be 60 times that. So the angular, well, let's figure out, how did we figure out radians before? We took the 2 pi that it went, and we divided it by the time. So that means this one came out as 1/2 pi radians. So we have to figure out what time, or x, would be equal to that. We multiply both sides by x. We divide them by 1.2 pi radians. So x is equal to 2 pi divided by 1.2 pi radians, which means the word pi disappears. And we're going to be left with seconds. 2 divided by 1.2. 1.6666. So x is equal to 1.6 seconds. So it travels that much inside. Or if you want, x is equal to 1 2/3, or if you want 5/3, or sorry, 1 2/3, or if you want 5/3 seconds, it's more accurate, right? How many revolutions does the thing take to do 1 minute? Okay, I'm going to take A. Since it takes 5.353 seconds to do 1 revolution, 60 divided by 5/3 is the same as 3 times 60 over 5. 5 into 60 goes 12 times. 3 times 12 is 36. 36 revolutions. I'm not sure of that answer. You should check. What is the radius of the wheel? That's a good question. So, if it has traveled 9.6 seconds, 9.6 pi in 10 seconds, and we have to reduce this down. How do we reduce this down to 5/3? We would have to divide by 10, multiply by 5/3, right? That means we would divide this, meters, this by 10, and multiply it by 5/3, which is the same as 5/30. Hope that logic makes sense there. So I take 9.6. What do we do? We'll do it like this. 9.6 divided by 10 times 5 divided by 3. That's how many pi radians is the circumference. Sorry, oh no, that's how many meters it travels in 1 revolution. Then we can take this. 2 pi r is equal to 1 distance. Divide both sides by pi. 2 times r is equal to 1.6 meters. Therefore, r is equal to 0.8 meters. Someone might want to check all these answers in the back. Not 100% sure that I got them all correct. Yeah, here we go. It is indeed 0.6 meters, but it says it travels 36. 12A, it's saying 36. Let's get back there. I might have to do 12A again. How many revolutions does it take in 1 minute? So I got that wrong, I think. It's interesting that I got the radius right. How many revolutions does it make in 1 minute? That's how much it makes in a second. So in 1 minute, we can just try that again. 1.2. If it does that many radians in a second, and in a minute it does this many radians. Yeah, no, I didn't get that right. So how many revolutions does it make in 1 minute? So I'd have to figure out what it's, I thought I did figure out it does 5 divided by 3 pi revolutions. Or 5, I thought 5/3 was it. So let's take 60 and divide it by 1.66. 36, yeah, there we go. That's the answer. If it does 1 revolution in 5/3, then in 1 minute, you take 1 minute and divide it by 5/3 and you get 36 revolutions. See if I can get it even more accurate. 60 divided by 5 times 3. Yeah, 36. 2 pieces of mud are stuck to the spoke of a bicycle wheel. Piece A is closer to the circumference of the tire, while piece B is closer to the center of the wheel. Do you believe the angular velocity is the same? What's different is the distance traveled. That's an interesting question. Okay, to get back to this, yes, the angular velocity will be the same because even though it's further out and traveling a greater distance, it's traveling through the same, a different radian measure. You can fit more radiuses on the outside than this one. In other words, the radiuses that B is traveling is the same as the radiuses that A is traveling. Therefore, the angular velocity is the same. Is the velocity which A is traveling greater than, less than, or equal to B? It's greater than, because it has to travel greater distance in the same time. They both go around in 1 revolution, but B is closer, so its circle is closer to the center, so its circle perimeter is smaller, and therefore it is traveling a smaller distance in the same time than this is. If the angular velocity of the bicycle wheel increased, would the velocity at which piece A is traveling as a percent of the velocity at which B is traveling increase, decrease, or stay the same? If the angular velocity, so if it's sped up, as a percentage of B, I think it would stay the same. Not 100% sure. See, in your notebook, sketch the diagram shown and label each angle in degrees for 1 revolution over here. Then express each of these angles in exact radian measures. Oh, like that. Okay, no, I'll let you do that. You don't need me for that. It's an important exercise. But, okay, 30 is pi over 6, 45 is pi over 4, 60 is pi over 3, and 90 is pi over 2. And then you just add it. For instance, pi over 2 to this one's 60, it's another 30 degrees. So you take pi over 2 and you add it to pi over 3. And you use your common denominators and you just keep going around that. Once you have these first 3, you can just add them to the last one to get to the next one. I'm going to skip this because it's a triangle one and maybe I'll squeeze it in later.